Okay, stage is yours, Benedikt.
Romeo, let me just share my screen. Hi, so Romeo asked me to talk a little bit about the Claimed component compiler. So I guess you guys are familiar with Claimed, and basically the component compiler creates operators for the library from Claimed. So you have like source code, you just run the compiler, and then you get like production ready container images and different files like Kubernetes job files and so on to run this images. So this is basically the idea. So if we look how it works, it's basically that you have like some source code. So this could be Python, could be now also R script since last week, or notebooks. And then you run the compiler and you basically get different Kubeflow component YAMLs, Kubeflow job YAMLs. You have a CLI tool from Claimed to run it. And in the future, we also want to support other runtime engines like LSF. And maybe for you, for information, so I'm basically doing currently an internship at IBM and basically supporting Romeo and developing Claimed. And we're mainly focusing on C3 in the last weeks. And basically how this compiler works is that you have like your source code and you just have to follow 4 different steps, and then you can basically run this compiler to create the container images. So here on the left side, we have an example of a code which just generates random numbers as an example. And you basically can provide all the information the compiler needs to build these images within this code. So for example, the name of the file itself is going to be the component name. Then you have like the first doc string, which becomes the description of the container image and the operator. Then you can just add pip install comments so that that Docker knows how like which packages to install. And the last step is that you basically define an interface with environmental variables, which you can also parse in different types. And so the compiler knows which parameters you need to run it. So for example, here we can define a number, and this number is going to be the number of random numbers which are generated in our code. And then here in the code, you can basically run whatever you want. So this was basically the approach which Romeo already presented last week. And we also have like an extra compiler which generates a grid wrapper. So this is basically able to scale your code across multiple workers by creating different batches or partitions of your code. So if you have, for example, input data, you can basically split up this partition either by providing a batch file, which basically includes the names of all the batches, or just by providing a group by string. So this is basically code which groups your images, not your images, your files according to the pattern you basically define. And so you can basically partition your input data, and then you can scale this data to multiple workers. So like can run, I don't know, 100 different workers in parallel if you have like 100 partitions. And we have different coordinator scripts, which are basically metadata of this coordinator. And then you can basically scale up this, and each worker knows on which partitions currently other workers are working or which partitions are finished. So you never process basically a partition twice. And if you have errors in one partition, you get the error files and you can just rerun it. And it will only process the partitions you have errors in after you basically fixed it. And they will all save the results. And you can basically run this either locally. So basically if you have like local data in a PVC, or you can also run it on COS. So basically we have a COS version, which basically downloads all the relevant data for this specific partition, runs the process, and then basically uploads the data in the end to COS again. So this is also a version. And to build this grid computing pattern, you basically have just to implement one extra function in your code, which basically gets the additional information you need to run it. So we again have this generate random numbers and all the code we already saw 2 slides ago. And then we have to define one extra process, which basically handles the execution of the sub-process. So in our case, we basically call it a grid process. And this is basically parameter you provide to C3 so that C3 knows which process to run in the grid wrapper. And this process takes the batch ID as the first argument, and then all your interface arguments in the same basically all arguments. And then you basically have to do 2 steps. So the first step is that you have to update your arguments based on the batch ID. So for example, if you have like an input path, you could add the batch ID to the input path so that the sub-process knows, okay, I only have to process this specific input files and not all the files. So here, for example, we just take the batch ID, which should be integer values, and we write this integer values into this new numRandom, or basically we overwriting this function. And then the next step is that you basically execute your normal code. So mainly you should have like a main function or some other function which basically includes your code. So you definitely should put all your execution code into a function so that it's first executed with this updated parameters. And that's basically all you have to do to run this grid pattern. And the grid wrapper from Claimed basically adds some additional parameters. We have had a look in a moment, which are basically added automatically. So that's basically all you have to do to run this grid computing pattern. And let's have a look at some code so that you also see that it works. So here, for example, I have now just a hello world script. So this basically follows the requirements we just saw. So we have like the name, we have the description, we don't need any pip packages. We define the interface, and then we basically have the main function, and we just execute the main function with the name, which is provided by the end variables, and then we print out hello world. And here we have this grid process. So this basically takes the batch ID, we update the name and just add like from batch ID, and then we execute the same. And so now we can basically, let me make this a little bit bigger for you guys. We can basically create the operator by just running C3 create operators. We define the script we want to process, and then we have to define a cloud container registry. So in this case, I just use my Docker Hub registry, and we can run this. And then it's getting all the information it needed here. So for example, here we see, okay, we didn't provide a description for the interface, but this is our name, this is our description. Here we have the input parameters. So always a log level gets added. And then we have the name here. Now it's building the container image, and then it's pushing the image to the container registry, and that's all. And we see now different files who are getting created. So for example, here we have the Kubeflow component YAML. So you can basically use this YAML to build your pipeline. You basically don't have to add anything here. Or we have a Kubernetes job YAML, which you can use to run on a Kubernetes instance. Just with OC apply, you just have to change basically these parameters, and you're ready to go. And to create the grid wrapper, we have another script basically, which, as you can see, this is all the same. and we just add this process. So this is basically process or just P, and we define the name of this process. So we run this one. So this also takes a minute maybe, or it's faster, and we have basically the same result. So let's have a look at, for example, the Kubernetes job YAML to see which parameters are getting added. So here, for example, again, we see the log level, and here we see all the different parameters who get added automatically. So here, for example, we can define the batch file, which includes the different batches. So for example, here I added a sample with like 5 batches, or we can also define other parameters. So for example, where the coordinator is for coordinating the different partitions. And if we want to run this locally, we can basically run this here. I just like mount basically this data folder, define a name, define the batch file, and where the coordinator should save the files. It's important that the coordination files are basically shared between the different partitions, and then we run this image. So let's do this. Oh wait, I first have to delete this actually, so that you guys see how it's running. So this might be a little bit small. So first we have basically a staggering start. So if you would run this operator in parallel, we don't want that all the operators access the files at the same time. So that's why we're waiting some seconds. By the way, if you basically want to run it on Kubernetes, you basically just have to define how many pods you want to run. So there's this parallelism. It's probably wrongly spelled. Parallel. I think it's like this. And then you can define how many pods you want to have in parallel. Okay, so now it's basically done. So we see here that it's loading this list here. It has like 5 batches, and then it's basically processing each batch after each other. So for example, here we have batch 1, batch 2, and so on. And if we would have like 5 container images in parallel, we would see that basically every container would process a different batch, and then we get like a summary here in the end. And we can see in the coordinator script here that we basically have this .processed files, which basically is telling all the other processes that they should not process this partition. So that's basically the idea behind this grid wrapper, and that's basically all from the demo. What we also built for the claimed library is that you could basically build such code, and then you can just push it to the shared repository, and then these operators are getting built automatically. So if you create like a config file and say grid wrapper true or cos true, for example, then it will automatically generate this grid wrapper patterns and do this automatically, push it to a registry, and also add the kubeflow YAML files and Kubernetes job files to the public repository, and you can basically deploy it on Kubernetes, kubeflow, or with CLA. And yeah, if you want to use this yourself, you can just install the package with pip install claimed, and this will install basically C3, and then you can create grid wrappers yourself. And that's all from my side. And yeah, I'm open for questions from you guys.
Questions, comments, complaints, questions? Is it useful to anybody? Okay, then thanks for your attendance. I'll stop the recording.